Now, given our definition of state transition systems and execution, we are going to look now look at what's the definition of asynchronous and synchronous systems. So remember, an execution is an infinite sequence starting from initial configuration and applying events one after the other. So we will define now the notion of applicability of an event, and it is a very simple notion. It's basically saying that a computation event first can be represented as a triple with state S1, S2, and an I, which means that this is a computation event by process PI, and it is performed on the state S1 and resulting in a state S2. And we say that this is a computation event if f of process I maps state S1 to S2. Now, just a very intuitive notion of when an event is applicable. So we say a computation event is applicable in a certain configuration if actually the node J happens to be in state S1 in that configuration. If we look now for the applicability of delivery events, so we say a delivery event from node I to J of a message M is applicable in configuration C if M is actually in the output buffer of node I in the configuration C. This is easy, you can see it here. Here's an example execution where we can see an applicable computation event. This computation event described by this way is applicable because we have the input state. The input buffer is that is the input buffer, and that is the output buffer. And the event will transform the state of P2 from this state to this state. So, if an event is applicable in a certain configuration, we say then applying the event E in this configuration will give us a new configuration after the performing the event E. So if we are in a configuration C or C1, applying E on C will give us a new configuration C1, say, new configuration C2. So now let us look to the asynchronous model. And the asynchronous model, our processes are deterministic, as we described by the state transition function. Given some message, we update the state and send messages and wait and continue. And the non-determinism comes from the asynchrony of the whole system. In this following sense, we can have a system where we have the state of many processes here. So this is the state, we call it of process P1, P2, P3. So at any configuration, we can perform a computation event in any one of the processes, and that's why it's there are possible computation events that can be performed, and there are also possible delivery events that can be performed. And we can, in different execution, choose one or the other. So in one execution, we choose a delivery event over, say, a computation event, and so on. So that actually gives us a situation to model that messages takes arbitrary amount of time to be delivered and processes execute at a different speed. So what is, in the asynchronous model, what we define something called a schedule. And a schedule is a sequence of events. Okay? So event synchrony is determined by when we perform a delivery event, and process speed is determined by when we perform a computation event. And so all non-determinism is embedded in the schedule. And the schedule, there are many different possible schedules. So given an initial configuration, the schedule determines the whole execution. And as we know, the schedule, not all schedules are allowed in the initial configuration. It's only the schedule of applicable events. In fact, at any configuration, we can only schedule applicable events. So what's admissible execution in the asynchronous model? In the asynchronous model, an execution is valid, or we call it admissible, if each process has an infinite number of computation steps. We can always perform a computation step on a process, because a computation step can also be dummy. It can ignore incoming message, just perform dummy local computation, and it might not produce any output messages. So each process has an infinite number of computation events, and each applicable computation event is actually performed, is eventually performed. So in a schedule, in the sequence of execution, all computation events are eventually performed. And each applicable delivery event is also eventually performed. So it means we cannot delay a process indefinitely, or we cannot delay a message in the network indefinitely. So why we talk about infinity, in the sense that each node has an infinite number of computation events? Well, we would like to distinguish between between nodes that are running and did not crash, and node that will eventually crash. So a correct node, a node that is running in the system, will always have some events to execute, some computational events. And even if the algorithm finishes, we can say that the nodes perform dummy transitions or dummy events. So that is the asynchronous system. The only thing that it matters for us in the asynchronous system was we could delay execution of computation events and delivery events at arbitrary amount of, say, steps, but eventually they are executed. Now we look to the synchronous systems. Synchronous distributed system execution happens in log steps, and execution are partitioned into non-overlapping rounds. So what happens in each round? Informally, in each round, each process can send a message to each neighbor. So you start by, and all messages are delivered, and every process computes based on the message received. This is what happens in each round. Okay? To say it more exactly, in a synchronous system, execution is partitioned into disjoint round, and a round consists of deliver events for every message in all output buffers until all output buffers are empty. So we start by delivering all messages. And then we perform completion events on each process until all input buffers are empty. So this is called a round. And in a synchronous system, every execution is admissible, but it has to obey the constraints on first deliver all messages, do computation, and then do computation steps. And every process takes an infinite steps, and every message is delivered. So we see it here. So again, so you can think of the execution happens in round. So round 1 followed by round 2, followed by round 3, and so on. And what happens in each round? So you deliver all messages, perform computation steps in all processes, and that will produce new message in the output buffer, and then we continue to the next round. So one way of seeing this is, you can see if you look to an execution and we look to a round, you start by delivery events and then comp events until no more comp events that can be performed, and then this is round I, and then you continue with the next round, round I plus 1. Okay, that's it. Thank you.